So there is a discontinuity at 1, of course.
Yeah.
No.
Oh yeah, 1, 2. Can we? 1, 2, 3, and 5. Oh, but 5 is the end point, so we don't have 5 either. Thank you. We're only looking in between 0 and 5, but not including, because there would be 1 and 0 also, and 1 and 5. But we just get rid of those. 1, 2, and 3 have discontinuities. And now the point at, we want to violate the first one. The first rule in the checklist is that the function has to actually be defined there for it to be continuous. The function apparently is not defined at 1 or at 3. At 2, there is a definition of, see, f of 2 is 1, so that's fine. So only 1 and 3 don't have the first point. The second condition is the one that the limit has to exist. And the limit exists at 1 because from the left and from the right, the limits agree. They're both going to infinity. So the limit at 1 is infinity. That one technically counts as a limit. The limit exists on 3 because the limit is 2. From the left and from the right, they're both going to 2. At 2, there's a big problem because the limit from the left and the right are different. From the right, it's coming into 1, and from the left, it's coming into 2. So there's no limit here, which means 2, x equals 2 violates that one. What? There can be a technicality that will say the limit doesn't exist for 1 because it's infinity. To violate this point of the checklist, just to get it right. Oh wait, I said 2, but did I mean? Yeah, I will just add 1 and see if this takes that. And so there's an argument to be made about whether this one violates the second point. Because apparently the limit is 2. Limit as x approaches 1 of f of x is infinity, and so that should satisfy condition number 2, but I think we could restate condition 2 to make it less ambiguous. We could say limit as x approaches a of f of x equals L for some real number L like this. This is a tighter condition for number 2, because now it disqualifies infinity as being the actual limit that exists there. This should be condition number 2 from now on. And then number 3, condition number 3, the limit has to be what the function is defined there. So, is that any of them? Do you feel like any of them violate the third point? There's a bit of a question about this one because the limit is infinity, but the function is undefined there. But we already said that that point violated the first condition because f was not defined. What do you think? Do any of the points violate the third condition? That the limit needs to be the same as the function value? And I'm wondering, does that necessitate that there is a limit and that the function is defined there? Because otherwise they all break that. Because the function value is undefined, but the limit is infinity. Here the function value is 2. So at least 2 must be violating it. But that one has no limit. No limit doesn't equal 2. Oops. And then what about at 3? The limit is 2, but the function's undefined. I'm gonna see if it takes B real quick. Yo. then otherwise it seems like it's all of them. Let's see if it takes that one. Go away, but I want to see this diagram. Generally, are you satisfied with this one?
Yeah.
Very good. Oh, we're missing Ahmed, huh?
I'll tell you what's the bathroom.
Did he took his backpack? I thought there's no backpacks in the bathroom.
It's probably sitting in the hallway.
Generally, he can't tell a lie. But the other's personal best is pretty nice. Y'all want to see any other homework problems? Okay, then let's finish up 2.7. If we finish up 2.7, here's going to be the strategy. We're going to do 2.7 today. We'll do test review tomorrow and Thursday. Yeah, Monday we'll either continue test review or we'll talk about something new. Monday is a wild card. Test on Tuesday.
We should go into limit theorems.
Yes. Limit theorems. Wait, is that one of the sections? 3.1 should be, I think, talking about derivatives. We've seen a bunch of limit theorems in this. Did you see a section called limit theorems? Oh, nice. Yes, we've been seeing a bunch of limit theorems. What was the last limit theorem that we saw? Theorem 2.1 is about limits. It's how, the limit from the left and right have to agree. That's an example of a limit theorem. Squeeze theorem, that was a limit theorem. It's about the squeeze. Linear functions have limits where it's just defined. You just do direct substitution. That's a very lit theorem. So, we have to prove this limit. And so, do y'all feel hyped for proving this limit based on what we did last class? Because the last class we proved the limit also. And I want to draw a distinction right here between finding or calculating a limit, calculating, computing, finding / calculating limits versus versus proving limits. Two majorly different ideas. Because calculating limits, we've been doing it all the time so far in this section. Or in all these sections. In the whole chapter 2, we've been finding a bunch of limits. And this is one that we can find so easily because we have a theorem for this limit. Since it's a linear function, we can just plug 4 in there, and it's going to go 4 times 4 is 16 minus 15 equals 1. So this limit, it's no big deal to find it. It's a problem with proving that that's what the actual limit is. Now, proving this limit, we would never care in the IRL to prove such a limit as this, the one that's in the problem at hand. Proving that this limit is 1, it is trivial in nature. And it's not that important of an idea. But the things that go into proving this limit, they actually are useful, and they prove the modern theoretical foundations of calculus, which is that calculus, like areas under curves, they're based on limits, and we should want to prove things like prove that if you take the limit of what you can call the, well, there are many names for this thing. There's something called a Darboux sum. Darboux. Any French speakers can tell me how to pronounce this one. But I guess should be something like, wait, but which one is it? Does anybody take French?
I know it's Darboux.
Okay, so this Darboux sum. There are lower and upper Darboux sums. And the Darboux sum you get by breaking up the area underneath a curve. You get the lower sum by breaking it up always by choosing the height of the curve to be the minimum that the curve achieves on the little subinterval that you divide it into. And you find the upper sum by always defining the height of the curve by the max. And so in case of the increasing function, you can call it by a different thing, which is called left Riemann sum, like this. Versus on decreasing interval, it's called right Riemann sum. Because always the right side of the interval has the height of the rectangle. That works when it's decreasing, when it's increasing, you have to take the left one. This gives you a lower Darboux sum, as it were. You could do the same curve, but you can find the upper Darboux sum by always using the max on the interval, which would be a right side Riemann interval, or right side Riemann sum in the case of the increasing part, and then where it's decreasing, you should use left interval, so that the rectangles are always hanging out. And then this one, making these rectangles. And so this gives an underestimate, this gives an overestimate of the area. And what you would be interested to prove, if you're trying to prove that integrals work, is that we would, as opposed to this problem that we're about to prove the limit, we would like to prove, and let me say that if you add up this one, you find the Darboux sum, I'm gonna call it L like this, because it's the lower, I'm gonna call this one U because it's the upper. We would like to prove that the limit for L is equal to the limit for U, and it's equal to the area under the curve. And so in a very technical sense, we will or would prove areas, not in this class though. It would be in a different class. There's a class called analysis where you can do it. Analysis is the name of the type of math that we're actually doing right now. We're not doing calculus so much as we're doing analysis. It is a branch of math. Just like there's algebra, geometry, calculus, there's one called analysis, there's linear algebra, topology, abstract algebra. There's a lot of branches of math, differential geometry, number theory, arithmetic, graph theory, many branches of math. We're doing analysis when we're doing these epsilon delta proofs. And inside of analysis, you can prove everything having to do with calculus. There is some controversy though, if you can believe that limits can be controversial. There's some controversy about the theoretical foundations of calculus, and people just accept them as it were kind of like a religion. Modern math has some type of feel of being a religion because people accept things which someone just told them and they believe it to be true, and maybe they don't question it. But let's see about proving this limit. We're just going to accept that all of this stuff is true and that it works. And so let's see how it works. The limit, we're trying to prove that the limit is 1. And so the limit's always the y value. We're trying to prove this one. And we're trying to tell how close f of x gets to this thing. F of x is the y value, 1 is a y value. And so we want to make this structure with the absolute values the difference. This is giving the distance between f of x and L. That's the absolute value of the difference. It tells you how far apart they are. And we want to ensure that how far apart they are is smaller than any number that you can think of. And that's what the number epsilon is representing. It's representing any small number. It can be as small as you want, and you can think of it as being the smallest imaginable number. We understand that there can be numbers smaller than epsilon. You can take epsilon over 2, for example. Epsilon over 4 is even smaller than that. And epsilon's really small, then 1 over epsilon squared should also, or actually I guess just epsilon squared should be smaller. Numbers less than 1, when you square them, they get smaller. Bless you. And so there are many numbers which are smaller than epsilon. That's not really what we're trying to say. And that's how this differs from the approach that people used to have when calculus was first invented, of using infinitesimals. Because an infinitesimal was literally, that was the idea, was this is a number which is smaller than any other number. And then you carry on proving based on that. What we're saying about epsilon is this can just be any number. It can be as small as you want, or it could be big. It could be like 100, or it could be 1. Or it could be, 1 times 10 to the negative googolplex or something like this. And so that's what we're doing. We're trying to tell how far apart f of x is from the limit, and we want it to be extremely small. That's why we say that the limit is that, because we're like, they're so close it's indistinguishable. It's similar to the idea, even though it's a little bit different. This idea that if you do 0.9 repeating like this, that's the same thing as the number 1. It's because these numbers, they're indistinguishable. You can't say how far apart they are, because if you say how far apart they are, they're actually closer than that. You just add more 9s. And they're closer than anything that you could say. And so we want to say that the function value and the limit are kind of like this relationship, that they get as close to each other as possible. And we're going to say that that happens as long as the x value that we're plugging into the function is close enough to a where we're finding the limit. We're finding the limit as x approaches a. If that's close enough, x and a are close enough, which we put this sufficiently closeness we call delta. If x is sufficiently close to a, then we can ensure that the function value is arbitrarily close to the limit. And so when we saw a description like that just in plain English, this is how to make it in symbols. And so here's how the proof should go. Off to the side, we're gonna have to do some work off to the side. And that's pretty customary in a math proof. You do all the work over to the side, and then you write it up neatly, so all the steps just flow, because you already figured out what number should go where and everything like that, and so the proof just flows. And what we're gonna have to find off to the side is what this delta is. How close x needs to be to a in order to ensure that f of x minus the limit is less than epsilon. In our case, we have f of x, it's this guy, 4x minus 5, that's f of x. And identify that one. That's f of x right here. The 1, that's the number L from the definition. The 4 right here, this is a, little a. And epsilon is arbitrary, so we can use it as a variable. It can just be whatever anybody wants. And then delta, this is what we need to find. Need to find as a function of epsilon. So that if somebody supplies any arbitrary epsilon, then we could give the corresponding delta. In this case, you can almost predict something about it. You'll see that there's a pattern about the epsilon and delta because of the way this function is. It has a slope of 4. So it's like if you want to be within some amount in the y direction, you only need to be 1/4 as close in the x direction. Because every time you go over by 1, you go up by 4. And so we can predict, maybe delta could be epsilon over 4, it would work. I think it would work, but we will find out. Do you guys know what arbitrary means, by the way?
Yeah.
What does it mean, Nahum?
Like, arbitrary is like, to me it's like, relative, I guess, is the closest thing that I can do, maybe.
Arbitrary. I've been using this word so much, but maybe it obfuscates the definition if we all think arbitrary means something else. Anybody want to tighten up Nahum's definition? What does it mean, arbitrary?
Alex has an answer.
What is it?
Alex has an answer.
Let's go, Alex. Alejandro.
Something that's just Going on forever.
Going on forever. Colby.
It's very loose, especially like there's no set value to it. It can be really whatever you make it.
Yes. Arbitrary, it comes to the what you have to do to choose it. It's like what Colby said. It's very loose. It means chosen for no particular reason. It's like
random.
yeah, random. Random's a nice one. Arbitrary. So any random epsilon it can be. And that's, we're gonna say, somebody just says how close they want the function value to be to, in our case, 1. Then we just say, well, as long as x is within some amount of 4, like maybe it needs to be within a quarter of 4, so between 3 3/4 and 4 1/4. If we're inside of that little window, then we can ensure that the function value will be satisfactorily close to 1. So let's see it. All right. Here goes this one. We'll write this first because this is the condition that we're trying to satisfy. Is that f of x minus L, we want it to be less than epsilon. We must satisfy this thing right here. And we can plug in all the stuff that we have because we have f of x goes 4x minus 15. Oops, I don't want to already chop that one. I need to put minus L. Minus L is 1. So the difference between the function and 1 needs to be less than epsilon. And then we're trying to obtain from this one. I wonder, it always seems like a coincidence how it comes out so nicely. I want to just simplify this one a little bit. 4x minus 15. The minus 15 minus 1, this in parentheses doesn't do anything, but I'm gonna write it anyways. 4x minus 16 we have. And keeping in mind right here, here's a thinking person who's looking at this problem and they're thinking, we want this, we want a value to put here, the difference between x and 4. We want a value for this delta right here. So that's what the thinking person is saying. We want a value to put right here for delta. We want to see the absolute value of x minus 4 needs to be less than delta. And what to put for there. What to put for delta. So if we can make this thing, the absolute value of x minus 4 appear in this work, then it will be helpful. And do you see that it's about to happen? Because here we can factor out a 4. 4 can come out of absolute values, no problem. We can divide by 4 right here. So it goes absolute value of x minus 4 needs to be less than epsilon over 4. Since we got here by algebraic steps, we could always reverse the algebraic steps. And so it's like we did a little dive down, and then we backed back up, because now we found out if this is true, if the absolute value of x minus 4 is less than epsilon over 4, we can just reverse all of these steps and end up here. That the difference between the function value and 1 is less than epsilon. It came straight from here. So now we just want to posit that this is our delta value, epsilon over 4. We would choose this for epsilon. Take delta equals to epsilon over 4. And if we do it, we would put that at the beginning, because that's actually where we start. We start the proof saying if x is this close, so now we're actually ready to do it. We can write the proof right here. It's going to be little. I'm way zoomed in. This piece on my page is like a 2" by 2" thing, but it will fit. Okay, so we will let epsilon greater than 0 be any number, or any real number if you like. will say this one then for delta equals to epsilon over 4. We have absolute value of x minus 4 less than delta. Implies that this one, x minus 4, is less than, we can put in our delta value, epsilon over 4. And we're going by implications, going, if this is true, then that's true. If that's true, then this is true. If this is true, then that's true. And that's why we're having all these arrows. These arrows are a shortcut of saying if-then statements. Here started out with a then, but this also has a feeling of a conditional statement like an if-then. Okay, so now I want to multiply both sides by 4. So it's going to go 4 times x minus 4 is less than epsilon, which goes, here the 4 can go on the inside, 4x minus 16 is less than epsilon, which we can change this minus 16 into the minus 15 and minus 1. 4x minus 15 minus 1 is less than epsilon. That's what we wanted to show, was this relationship. And so then we can say finally, so the limit as x approaches 4 of f of x is 1. And this is the end. And so these would be funny maneuvers to do in real life. Putting the 4, multiplying it in there, separating the 16 into minus 15, minus 1. This didn't just come from nowhere, it came from this process of figuring out which epsilon to use, or rather which delta to use with respect to epsilon. We found out delta should be epsilon over 4. And then we can see in here what some of those steps were, like here, the minus 15, minus 1 becoming minus 16. And we're literally just undoing these steps coming this way. That's how the proof was. It was those steps in reverse order. Starting out, because we're supposed to start out with this condition. The way the limit goes, it says if x is sufficiently close to 4, which we're saying this is going to be sufficiently close if we make it be within epsilon over 4. If that's true, then the function value is within epsilon over 1. And so we prove the limit. Feel like you can do one? I know you can do it, Logan. Just believe in yourself. I believe in you. But do I have one? This limit, proving that the limit is actually equals to infinity. Very similar. Go see this example together. But to be able to do it, you have to do it yourself. You have to try doing it yourself to figure it out. It's impossible to watch me do it and then be able to simply reproduce that. I wish that we could see some other kinds of interesting limit problems. I always just feel like going off on tangents and talking about random stuff. By the way, how was math club today?
It's good.
Yeah. Anybody who missed math club, y'all missed out.
We reviewed some of the homework.
Yeah. We looked at some homework a little bit. We talked about cool stuff. We did riddles, thought experiments. So what are we doing now? This ought to be an interesting one. If you say that a limit is infinity, and we want to prove that the limit is infinity, that means that if you pick any positive number in any big here like this, you just pick one of these, this becomes the arbitrary thing, is how big you want it to be. There exists some corresponding delta, which can be small, such that the y value of the function is going to be bigger than however big the arbitrarily large number you said was. The function value will be even bigger than that. And that's how we're supposed to say that the limit's infinity, because it's bigger than any number that you can name, and that's what we're calling infinity in the first place. It's bigger than any number that you point to. And we're going to say the function value can do the same thing. It can be bigger than any number that you want, as long as you're within delta of an a. And so here we're wanting to prove this one, that the limit as x approaches 2 of 1 over quantity x minus 2 squared is infinity. And so we want to start from this thing, that there's going to be some number in, like this. And here I'm just doing a little bit of scratch work on the side that will build us up to the actual limit thing. Because we want the implication to go like this, that I'm going to load up some symbols at the front, which is that for every number in that you can pick, there's some delta such that if x is within delta of the number a, which is weird saying it out loud while writing it because a goes first and then delta, but this means that a is within delta of x, or right here the distance between x and a is less than delta. That will imply that the function value is more than n. We're trying to prove this thing. So we want to start here. This is supposed to imply this, but we need to be creative about which delta to choose. Delta will be based on n most likely, this big n. It will be a function of this. We say if it's delta is at least like 1 over n or something like this. And so we're starting with some number n. We want it to be the case that f of x is greater than n. F of x, we already have a thing for this, 1 over x minus 2 squared. We want this to be more than n. That's what we're going for. Here we don't actually need absolute values. Can you tell me why?
Because it can't be negative.
Yeah, it can never be negative. So we can just drop those. It's fine. Okay, so now we should notice we're looking for something the same way the other one we were looking for something that had to do with the x in absolute values. We want something like x minus 2 instead of absolute values. We want some bound for this. We want over here some function that has n as the variable. And then we choose this thing to be our delta right here. And so we need to get x minus 2 by itself. Looks pretty nice. What if we divide by n and we multiply the x minus 2 squared over here? And then we need to take square root. But if we take square root, this is going to be a little bit odd. We need to figure out what to do about the plus and minus, because you certainly should have a feeling that there needs to be a plus or minus going on here. And so, plus or minus. If we can put it anywhere. But this is an interesting point to make, which is that the square root of something squared is the absolute value of x, like this. Have you ever seen it? If you think about putting in different numbers, it always works, because the square is going to make it positive, and square root always gives you a positive answer. Absolute value also always gives a positive answer. And so imagine you go through this procedure, you square something, it makes it positive. Then you square root, it just gives you the positive answer back from what you started out with. So like if you plug in 1, or maybe 2 is better, you plug in 2 squared, take square root of 4 is 2. But if you go in here with a negative, like negative 2 squared, and we take square root, it's also going to go square root of 4, which is 2. And in either case, you're getting the absolute value of the number that you plugged in. So we can replace this thing by absolute value. We want absolute value of x minus 2 to be less than the square root of 1 over n. So as long as x is this close to 2, which as n gets bigger, this value gets much smaller. We can even just call this one 1 over square root of n. It looks maybe a little better. They're the same. Square root of 1 is equal. So we choose this to be our delta, and then we can carry on with the proof. We can say, here goes the proof. Let n be any number. Take our delta value to be 1 over square root of that n. Since this one's arbitrary, it's already been given right now. It's just some number. So we can plug it into this formula, we get this delta. And we said, so now if this one x minus 2 is less than delta, which is 1 over square root of n, that means there are a few details that we could fill in, like this is a fact that could stand to be proven. If a is less than b, then a squared is also less than b squared. Could you believe that is always true? It is always true. I think maybe in this case a and b need to be positive. But we're about to do that. So now if we just square both sides, we're just going to carry on like this. Square both sides. This implies that this thing squared is less than 1 over square root of n squared. Which now that we're squaring the absolute value, we don't need absolute values anymore. We can change to parentheses. This is less than, we can square this one, it becomes 1 over n. Which we can do the shuffling, we can multiply the n over here. And then, if we divide though, yeah, that's what we wanted. Dividing by x minus 2 squared. The function value, that's what's there. The function value is greater, we have that one, I'm gonna reverse the order again. The function value is greater than n. So the limit as x approaches infinity, no, it's not as x approaches infinity, x approaches 2 of f of x is infinity. We proved that one. Could have had a few more steps just to clarify a couple of these points. Like this kind of thing in proof, sometimes you need to actually set it up to prove something like this. But we're taking many things for granted. And so we proved that some limit was infinity.